Hi, I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here. And I'm going to be, I hope, wrapping up this Knight-Darwin law paper, at least the initial draft of it this time around. And I think that'll be pretty quick because I think I figured out how to simplify the proof of this dual Knight-Darwin law. The last stream I thought I had figured out how to simplify it, and then I got stuck on an edge case. But I think I realized how to get around that, and it's quite silly. I should never have gotten stuck on it in the first place. And now, if that works, then that simplifies the proof so much that I think it doesn't even need a figure. So if so, this will be ready to be called done, at least the initial draft. And at that stage I would then let it sit and ferment for a week or two, send it to some friends to get feedback, that kind of thing. Now we'll copy the beginning of the proof. Up to there, I believe, should work. Let u1, u2 dot 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 be an arbitrary infinite directed path in S. We must show that some ui has multiple distinct children in S. By repeated applications of the Knight-Darwin law, there exists I1 less I2 less dot 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 such that each uij has more than or equal to 2 parents in S. Using the axiom of choice, for each j, let yj in S be a parent of uij other than uij minus 1. By assumption, no element of S has infinitely many children. It follows that the cardinality of the set y1, y2, dot dot dot. The cardinality of the set of yi's is infinite. And since u1 has infinitely many descendants in S, namely u2, u3, dot dot dot, the IAP axiom guarantees S has less than infinitely many non-descendants of u1. Since the cardinal of the set of the y's is infinite, there must be some j such that yj is a descendant of u1. Let's make that a k because we're talking about i's and j's up above. Now, by the assumption at the top of section, prelim section, yk has less than infinity many ancestors. Thus, there is some you know what, we're going to run out of variables. I think we can use j here. Some j such that yj is a descendant of u1. By the assumption atop the section, yj has less than infinity ancestors, thus there is some maximal k such that yj is a descendant of uk. Now, case 1 is that yj equals ul for some l. And this is the case essentially where I was stuck last time. And the way you would get out of this case is you would say that then yj itself must have 2 children, which would be as desired. Yj has children u sub l plus 1 and u sub I sub j. And these are distinct because y sub j is a parent of u sub I sub j emphasis other than u sub I sub j minus 1. Thus, L is not equal to I sub j minus 1. Thus, L plus 1 is not equal to I sub j. QED for that case. In parentheses, after saying these are distinct, we'll say proving the theorem. Now case 2. Y sub j is not of the form u sub L for any L. Now, if y sub j is a child of u sub k, checking something here. Yeah, if yj is not of the form ul, if yj is a child of u sub k, then u sub k has two distinct children in S. Oh, in case 1, I should mention parenthetically that ul plus 1 and uij are both in S. If yj is a child of uk, then uk has two distinct children in S, namely u sub k plus 1 and y sub j. Distinct, since distinct by the assumption of case 2. Assume y sub j is not a child of u sub k. Let's make that a but assume. But assume y sub j is not a child of u sub k. Well then, then it follows that u sub k has some child C, which is an ancestor of let's just say then u sub k has some child. Then since u sub k is an ancestor of y sub j, u sub k must have some child C, which is an ancestor of y sub k. By maximality of k, C is not equal to k plus 1. Thus, u sub k's has two children, u sub k plus, has two distinct children, u sub k plus 1 and C. It remains only to show C is in S. This follows by the convexity axiom. QED. Much better. Well, it's actually not all that much better, but I think I mean, it's not all that much better in terms of length, but I think it's much easier to visualize and so on, and so I think a figure is not needed. Let's try and compile this. Great. Now let's proofread that theorem. Theorem 9. Dual Knight-Darwin law. Suppose S sub G satisfies the convexity axiom and the IAP axiom. Assume that for every U in S, U has less than infinitely many children. If S locally satisfies the Knight-Darwin law, then S locally satisfies the dual Knight-Darwin law. Proof that U1, U2, be an arbitrary infinite directed path in S, we must show that some UI has multiple distinct children in S. By repeated applications of the Knight-Darwin law, there exist I1 less I2 less ... such that each UIJ has bigger than or equal to 2 parents in S. Using the axiom of choice, for each J, let Yj in S be a parent of Uij other than Uij minus 1. By assumption no element of S has infinitely many children, it follows that the cardinality of the set of Yi's is infinite. Since U1 has infinitely many descendants in S, namely U2, U3, the IAP axiom guarantees S has less than infinitely many non-descendants of U1. Since the cardinal of the set of Yi's is infinite, there must be some J such that Yj is the descendant of U1. By the assumption at the top of section 3, Yj has less than infinitely many ancestors. Thus there is some maximal case such that Yj is the descendant of Uk. Case 1, Yj equals Ul for some L. Then Yj has children Ul plus 1 and Uij, both in S, and these are distinct. You know, we should move case 1 up slightly because case 1 does not need K. So, in some sense, the proof is simplified by moving case 1 up above the definition of K. Case 1. Yj equals Ul for some L. Actually, in fact, we could move case 1 all the way up to being after the first paragraph of the proof. And then and what about the if Yj, yeah, we need K for that, so we'll just move the statement of case 2 up immediately following the case 1 paragraph. Let's proofread this proof now. Proof that U1, U2, be an arbitrary infinite directed path in S, we must show that some UI has multiple distinct children in S. By repeated applications of the Knight-Darwin law, there exist I1 less I2 less ... so that each Uij has more than or equal to 2 parents in S. Using the axiom of choice, for each J let Yj in S be a parent of Uij other than Uij minus 1. Case 1, Yj equals Ul for some L. Oh, bother, we don't have the J defined. Oh, so we need to move the paragraph defining the J. Wait. Oh, bother. Right, so we do need the paragraph defining the J to precede the case 1 statement. Although case 1 makes no sense if we haven't defined J. By assumption, no element of S has infinitely many children. It follows that the cardinal of the set of Yi's is infinite. Since U1 has infinitely many descendants in S, namely U2, U3, the IAP axiom guarantees S has less than infinitely many non-descendants of U1. Since the cardinal of the set of Yi's is infinite, there must be some J such that Yj is the descendant of U1. Case 1, Yj equals Ul for some L. Then Yj has children Ul plus 1 and Uij, both in S, and these are distinct, proving the theorem, because yj is a parent of uij other than uij minus 1, thus L not equal to ij minus 1, thus L plus 1 not equal to ij. Case 2, yj is not of the form ul for any L. By the assumption at the top of section 3, why are we using L? We haven't used k yet. So instead of an L, we should use k here. But then that means that well, then the k in case 2 will make that the L. Changing k's to L's here. Thus ul has two distinct children, ul plus 1 and c. It remains only to show c and f as follows by convexity. Recompile. Case 1, yj equals uk for some k. Then yj has children uk plus 1 and uij both in S, and these are distinct, proving the theorem, because yj is a parent of uij other than uij minus 1, thus k not equal to ij minus 1, thus k plus 1 not equal to ij. Case 2, yj is not of the form uk for any k. By the assumption at the top of section 3, yj has less than infinitely many ancestors. Thus there is some maximal L such that yj is a descendant of ul. If yj is a child of ul, then ul has two distinct children in S, namely ul plus 1 and yj, distinct by the assumption of case 2. But assume yj is not a child of ul. Then since ul is an ancestor of yl, then since ul is an ancestor of yj, then since ul is an ancestor of yj, ul must have some child c, which is an ancestor of yj. ul must have some child c, which is an ancestor of yj. By maximality of L, c is not equal to L plus 1. Thus ul has two distinct children, ul plus 1 and c. It remains only to show c in S. This follows by the convexity axiom. Okay, git commit this, git commit, simplify proof of dual Knight-Darwin law. Great. Okay, I think this paper is pretty good now. I'm gonna let it ferment for a week or two and send it to friends for feedback and comments. And assuming that no major flaw is found in that time, then when I come back to it, I'll update it and then send it somewhere. Maybe Acta Biotheoretica. Acta Biotheoretica is where I first published in math biology. Back in 2013, I published my paper, Infinite Graphs in Systematic Biology with an Application to the Species Problem. I originally submitted that paper, an early version of it, to the journal Cladistics, where it was rejected. The funny thing is, the version I submitted, I was trying to sort of play it low key. Like, I was talking about colonies rather than species, basically playing the very humble academic, sort of conservatively flying under the radar, very careful not to make bold claims. And that was rejected from cladistics. I then sent a version to Acta Biotheoretica, where I was a little bit more self-horn blowing one's own horn, like emphasizing in the paper, hey, this is why this is important, etc., etc. And then it turned out that at Acta Biotheoretica, the editor loved it so much, she actually flew me overseas to visit her for a week and work on biology with her there, work on mathematical biology with her and a colleague there. And that ultimately led to another paper in 2015, which was published in the Bulletin of Mathematical Biology with DJ Cornett and Ari de Bruijn. And I've traveled multiple times to Leiden since then and done further work with them. Wonderful people, these Dutch biologists. Anyway, that's all for today. I'm Dr. Samuel Alan Alexander, mathematician and philosopher. Please like, comment, and subscribe, and I'll see you in the next video.